So hello everyone again and Bismillah. In this video I'm going to show you the code of our algorithm. It's actually already published in GitHub Repository. It's called MuGONA Repository page. In there I will put the link to that repository in the description of this video, inshallah. You can go there, experiment on the code itself, you can play with it, you can put some pre-processed images, maps, and examine the code, push it further to its boundaries. If you find any problem, get in contact with us. Our emails are shown actually in the paper itself. So the code consists of various sections. The first section is in which we include the libraries that will be used, and we also initialize and define the functions that are the core of our code. So every single function that will be used is in this first section. We run it, it will take no time almost. It works very quickly. Then we go to the second section of our code, which is the beginning of the main. Now, in this section, you will find that we declare the directory of the map that we will be dealing with. So if you want to change the map yourself, just put the map in the file, in the folder of the same folder of the code, then change this name to the name of your map. And also, if you use another extension, just change the extension from here. I prefer you use PNG, but it's not a problem if you use JPEG or something else, as long as the image is processed as we want, everything will work. Now you have the spacing in here. It's in pixels. You may define your spacing as you want, but don't forget that there is a trade-off as you get. As you set the spacing to be less, the code will take more time. It will be computationally a burden to your computer. So set the spacing as large as possible, but don't remember that we have a condition on the spacing. It should be less than the least dimension of the smallest obstacle in the map. You may review that from our videos, or you also may review it from the paper itself. We also have the scale. It's a scale that gives you the corresponding meters from the pixels of the map. So your map is in pixels basically, but it refers to something real. It refers to meters. So let's say you have your map representing a 1000 by 1000 meter real map. So your pixel map is 1000 by 1000 in pixels, every single pixel will be referring to a meter. So the scale will be 1-to-1. And this is what we have in our case. But if you have different things, for sure this is for square pixels, but if you have different types of pixels, distorted pixels, rectangular pixels, I don't know. If you have your spacing, if you have your scale to be not one, other scales, you may change this from here. You also have the average speed or the constant speed of the robot. This is for the sake of generating a certain trajectory for your robot to be following. It's not that important, but if you want a trajectory to be generated, you have to specify this. Anyways, we ran this, I think. Yeah, we run this, and we get our map in here. This is the pre-processed map. It's, as we have mentioned before, it's white and black. White regions represent available regions for the robot to navigate, and black regions represent obstacles. So I will click in here saying that this is my starting node. Then I will select various locations for my robot to visit, and they will be my goal nodes. So the computer is acting a little bit slowly. It's because I'm running various things on it. Now you may notice that I selected the position or the location of my starting node to be a little bit hard. It's surrounded by many obstacles, from every direction, and this is to show you the efficiency of our algorithm. However, you may also notice that I selected the location of the starting node to be isolated from the goal node. So all goal nodes are in one direction, when compared to the starting node. So this is called isolated starting node, and keep this in mind because we will be using it. You may also have read this in the paper if you have already read the paper. So we go on and run this code in which we'll generate the equally spaced nodes. Now, yes, you can see that this code has generated several equally spaced nodes with the exact spacing that we have specified. You may also see the blue colored nodes. These nodes are the user-defined nodes that we have already defined. Those are the goal nodes, and this is the starting node. we will close this and go on to run the section in which the neighboring graph is generated. Now this section will generate the neighboring graph. It will define the relations between the nodes in the map. It will take some time because it's an exhaustive operation. It's an exhaustive process. So just be patient. And when you actually run this code, try to spare the computational capability of your computer for the code. Yeah, it took some time in here, and it generated. It showed us that it generated the neighboring graph. This is our starting node, and these are our goal nodes. Now we close this and continue to run the section in which the ordering algorithm is gonna take place. I'll run it right now, then explain something. Now in here, if the starting node is isolated, then you will put true in here. But if it's not isolated, if it's an unisolated starting node, you will put a false in here. And in this argument, you will put true if you want your path to be closed, but you will put false if you want your path to be open. Now it's, yeah, you can see that it has already ordered all the nodes in this. I mean, these prints show you that the algorithm was ordering the nodes, and I can show you, yeah. So this is the visiting configuration we had. This is the total path we had. It might be not the most optimal path, but it is at least a near optimal path that was generated by our algorithm. You can see that the robot visits all the go nodes, then goes back to the initial starting node. Now we close this. We may go further to smooth the path that was generated using cubic splines in the code that I have published, or you also may use the B-splines in the code shown in the paper itself. Now we have a smoother path. We have to, I mean, zoom in to show you. Yeah, you may see that the sections of the path has been smooth. You may face some problems. I mean, you may face some problems saying that the path is going through the obstacle. In this scenario, you have to run the algorithm of obstacle avoidance. I didn't include that certain algorithm in my in this video, so you may run it. The function is already attached at the beginning in the first section. This was my video. I hope you have had a nice, I mean, overview on the code. If you have any questions, you can ask me in the comment sections, and thank you for listening.